We're back for the
Yes.
people online. My name is Simon Veloso, and I'm going to be presenting the EMTP modeling of renewable integration in Chile Power Grid initiatives and challenges. This is what we've done, and what we're about to do in the next probably couple of years. I work for the Chilean operator, and I'm gonna, for the sake of time, I'm gonna skip the slides about the power grid and the operator, and it's time left at the end. I'm going to go back to it. I'm going to talk about completely model of the power grid, how it became, how it started in 2022, how it's ongoing, and what we expect from it in the future and in the coming months. Because of these outputs, we also asked EMTP to develop a couple of tools, which are these online static connection tool and the real-time the DSA or the digital twin. The first one is almost finished. We're going to launch it officially in the next maybe in August or September. We're still looking for testers, but it's all ready to be launched. Also, I'm going to show you the performance modes we've been working with Phasor and how we're planning to do some additional tests and how we're in the loop test, and how they are going to be integrated into the Chile Power Grid, the one that I'm showing you in the first part. So, as I said, everything started in August 2022. The operator released a directive stating that every owner of a power plant that has a rated power higher than 20 megawatts must develop and deliver EMTP models, not EMTP models. We at that moment make a commitment to not only to ourselves, but to the country that we had to make a decision. It consisted in two models actually. One of them is a white box model. And the reason for it is because we were planning to do it faster than a black box model. Didn't happen like that. That was the idea. But at the end, what has been going on is that the conventional power plants are easier to get into the white box, what the former presenter said. And they are excused most of the time to present a black box model. Because, well, a conventional system are not very intellectual protected. The second stage are OM models. The reason for this is because we think, and we tried later, but we thought at that moment that they were going to be faster, and now we know that they are. Actually, we tried several reformings from two vendors right now, and although they seem to be very complex models, they run much faster than the open one, the whole complete, when you have access to all the blocks and the detailed models are available. So this second stage is going very, very well. Right now, this is what we're projecting. Well, not only projecting, these charts show how we've been receiving scheduling in green of the models that are coming from everywhere in the country. So it's around 300 models. The blue ones are the ones that we already got or we've already received, and orange or yellow, I'm colorblind, but I think it's yellow, is the one that we are integrated into the power grid. This is going to take a lot of time. I said in the launch that we are a department of 6 people, and we're trying to integrate models as they did since 2005 in Chile. So we're trying to compensate 20 years of development model of RMS, but on EMTP. And so we're trying to make it on time. We're probably going to finish at the beginning of 2027. And this is as ambitious we can be. There are two charts because these are the white box model and these are the black box model. We already are we are testing both of them right now. And it's not very easy because it's very novel for us, for the country. We even prepare this form based on the experience the other departments have with 20 years of experience with most common practice to validate models between RMS and site tests. And also, well, some very specific particularities of EMT models instead of RMS, which used to be easier. But still, moving on. Before that, this was created manually. This is a single line diagram that John presented in his slide. I remember we started building it in 2019. So it was long ago. And back then we didn't have such great ambitions. So right now we're using it for a lot of analysis. We're carrying performing analysis on this model. Also very important projects like HVDC and the virtual line project were tested into this grid. The dynamic models were made by hand, and in some of the cases, we use also identification of parameter identification methods to fit the dynamic response. And after that, I wanted to show you this official study we did in December last year, where we were able to compare our other tool, other model in Power Factory against EMTP. We have pretty similar results, but the range of analysis is very limited in this case. And why? Because as this model was made manually, it has some flaws directly derived from performing it manually. And they don't match one-on-one. That's another thing. And Power Factory, the departments are working on it. There are around 20 people. No, it's not 20 people, but maybe 15 people. So it's a lot of people working on this model, creating the scenarios and putting their feet on the worst case scenario to analyze the behavior of the power grid. And this is the one you see in blue in every chart is the time series from Power Factory. And as I said in the launch to some of you, we've been practicing 1.27 short-circuit ratio. And this is in Power Factory. So when we try to match that model into our EMTP model, we don't know for sure if this, well, probably it's more than 1.27, but we don't know how close we are to this value. But for the time being, it was good enough. There are big differences here because in EMTP, the way of modeling surge addresses is very different from what they do in Power Factory. And this is why we see different stages of the same fault, because at one point the varistor is discharging, and then it's short-circuited because it's maxed out. But in Power Factory, you don't have that phenomenon. Still, we see pretty similar oscillations in voltage. No, that's active. But in voltage, you see these huge slow frequency oscillation that are pretty similar. And the part of the high voltage transmission system is very well modeled. So it's pretty accurate for the time being. What we are trying to do right now is that instead of doing it manually, we are building it automatically from the Power Factory. And we could have done it with CIM, but sadly in Chile, we didn't know CIM until now. So we are a little bit behind on it, but trying to compensate the time. We sort of created a script based on JavaScript from EMTP and Python on Power Factory, where importing all of the data, not only the static data, but also the hypothesis of the point of operation. And this is already running. I mean, it was running a year ago. The guys just told me that it ran successfully. The flat start is very good. We're using usually generic models for the dynamics. but we're gonna plug the new OM and the generic models that have passed all the tests who I mentioned before. And then this picture is only to let you know that this is not manually constructed. This is automatically done. The future is that, well, we already did this graphically, but we need to remove each bug on a like step by step. But this is not, that doesn't mean that we're gonna amend each error each time it happens. Once it solves, it's cumulative, and we're probably solving a lot of new problems that can come up in the next region of the country. So we win a lot of things doing that. We finally are creating a model 101 with the Power Factory model that 15 people are working on. Is automatically made, it minimizes error, can be run periodically for several operation points. And this is the beginning of a twin feature for what's coming next. This is what we did. It's only to show you a little bit that we have written several code lines and in both platforms through an XML. And this is when we found that CIM had done it perfectly. So right now, we're also working in the CIM standardization of the system. But in the meantime, we still can use it. And this also allowed us to prepare a Power Factory model to not contain any errors into the CIM. So it's kind of a cleansing method also. Not only we're trying to advance faster, but also we're trying to correct a model that has been constructed the last 20 years. And that means that it has a lot of errors. And not errors that nobody can amend, is errors that nobody saw, actually, because it's too many people, too many years. So with these models, not only the automated one and the manual one, we're using it as an input for the this study connection tool, which is an online tool that allows you, as John said, allows you to upload your model, plug it into our aggregated power grid model, simulate, take all the results out, and then you can destroy the virtual machine. It's very well done. It's a detailed EMT model of the system. We are protecting the intellectual property rights of the EMT models. The verification during the connection process is going to be streamlined, because right now it's not a requirement for the power plants to pass these tests, but it's going to be in the future. It's going to be in the next grid code. Not necessarily the grid code, but in the directives we're gonna release. This tool performs stability and dynamic performance, and considers all these kind of huge projects or more relevant projects. This is what it looks like. It's very simplified. I try to make it easier for understanding. This is a first step when we create the user. The operator creates the user based on a form you need to fill out, indicating rated power, point of connection, voltage of the point of connection. And after that, you're going to receive, well, the user is going to receive some files, 4 files that are created by this tool, the EMTP developed, which is called database manager. And it's very easy to actually modify these values with your particular power plant connected to, this is only for graphical representations, it's not the actual model. You connect it, you compress it, and you upload it here as a second step. The third step is only wait for the simulation process to end and download the results. It's pretty straightforward. The second tool, and this is just started, is also a detailed model of the power system, but it's going to contain, as we're done in a second stage, is going to contain the new models that are being plugged into the power system. So Yeah, well, the study system, the study connection tool also is going to be updated, by the way, with the new models. And this is basically a digital twin. And I think the most challenging part of it is how it communicates with the SCADA systems and the power factory system, because the three models don't match. Right now, they don't match. And this is a nightmare for someone that needs to perform like on real-time analysis. So for the time being, we're still trying to decide what we're going to use as a language between all the platforms. We're probably going to go, well, I can't say actually. I would like to go with CIM, but I don't know. It's a lot of decision making at this point. And we also need to keep in mind that it needs to be doable in the short time. But basically what it is the SCADA system will report on a real-time basis to the model. If it's one-on-one, it's pretty easy. If it's not, you can consider several assumptions to make it, to force it to be matched, you can say. And we run a list of contingencies and assess if the point of operation brings any condition, undesirable condition. And this obviously is going to be useful for the dispatchers, as at the first it could be an alarm, but we've been asked also what else can the dispatcher do with that, and also there's an analysis, a post. I don't like to call it post-mortem, but it's a post-process analysis. So maybe the tool or an after tool can propose directions, propose protocol, not protocols, but maybe easy decision making. Moving on to the grid forming, well, this is only to give context. This is what EMTP has developed on grid forming basis for the generic models. It's only 3 of them because we've also noticed that one of the best performance grid forming models is the one that is not here. It's the PLL based, but this one is pretty useful still. The droop control is the more basic one, the most basic one, but it has its challenges. This is the interface that model has, and we've tried this this grid test, which is based on the IMO set of tests. And although we know it's voluntary, and they stated that all of the requirements are very strict, but it's not mandated to meet them. But based on that, and with the help of Jose, and a lot of help from Jose, so we appreciate this, we've been able to run all the tests successfully, not only because we want to know what a grid forming does and what is, but also because we wanted to try it on the big power grid. As I said, the power grid is running in 120 something short circuit ratios, so it's a pretty weak grid. A month ago was finalized the auction process for short circuit values, where only synchronous condensers participated. But in the next one, we're trying to put this into the table. And the only way to do so is to make an evidence of what a grid forming can do. The generic model has passed all the tests according to stability and also what you expect on steady state after every maneuver. In this case, is loss of the last synchronous machine, the grid formants that are kept on service, provide or distribute power according to the droop characteristics, and the same happens on every other test on the IMO test set. I'm not gonna through all of it. Not gonna go through all of it. Maybe the most important ones are the 3. Yeah, this test is to try changes in the rock-off in the frequency, and also, you can see some oscillations, but this is due to the meter in the RMS voltage because it's also sinusoidal. But also the grid forming behaved as expected, and in some cases reaching the maximum current it was set. And this was very interesting to hear in this general meeting, actually. We know now that there are several ways of limiting current during these transients, and some of them are more stable than others. But still, this is actually pretty good for not only for the country, but for my team as well. The sixth test was to test short circuit as expected. And the last one is phase jumps. After this, I wasn't allowed to present the cases with vendors reforming because we're still working on it, and vendors must participate in the discussion before. But what we discovered, one of the things we discovered with those tests that I'm not showing right now, is that DLLs are very fast, very fast. To my sense, it was around 40% of the time it could take to model that it's not black box. The two vendors we tried are passing also all the tests. But yeah, we don't know what's in it. So we're gonna try all of them in the same power grid and in the bus bar, the weakest bus bars in the power grid. Additionally, we are trying not to create, but to propose three additional tests, or is in discussion. And the objective of this is to compare the performance between synchronous generators, not synchronous generators, grid forming and grid following under similar conditions. And the equivalent source we're using here is not ideal. It has limited short circuit, and it also has inertia, but it doesn't have any control. It doesn't have excitation or governor. In that case, and I needed that. I don't remember what's behind this logo, but it was powered from the steady state and the short circuit ratio. No, I remember the power for the test. So I remember it was 100 megawatts and short circuit ratio of 1.5. So it was 80 megawatts.
Yes. Well, you cannot see because of the symbol, right?
Yeah.
I can see it on the projection online.
Okay, thank you. So it was 80 megawatts, each one of them in their own isolated systems, and short circuit ratio
1.5.
1.5. And in this case, well, the blue line in every plot is a grid forming, which has much better performance than the other ones. And it's also worth notice that the red one, which is a synchronous generator, is a very fast machine. I tried to use the fastest parameters for the control I could set and before it becomes unstable. So this is as fast as I could get. And the next one is short circuit ratio.
1 and 80.
Okay, so maintaining the power, and now with a short circuit ratio of 1, we lose synchronism for the synchronous generator and for the grid following. And the grid following can maintain its set point accordingly. This is also, I remember this was 0.75 short circuit ratio, but with less power.
60.
Yeah, 60, because we're reaching critical voltage permanent stability. And in this case, also the grid forming can maintain its set point. Pretty good results actually. So the next step, well, this is a former step. This is the manually built power grid, but with the new grid forming tuning. And we have these results, which is an ongoing investigation. This is only with 70% of renewable penetration, and still pretty good. We're reaching in it's 4 grid formings, by the way. These 4 stars are here on the northern part of the country, and the 4 grid formings are performing according to what was expected. but 70% is something from the past for now, for us. Yeah, maybe I could go back to the statistics of Chile Power Grid. But 70% is something that happened last year on March. So this year is more than that, and it's going to be more than that because I get emails on each power plant distributed energy resource that is connected, and I receive every week a new connection. So it's going dramatically fast. But with 70%, it's good. Besides a paper that John and Jaime published this year, had similar results, and they're all publicly available. But right now, the next step is to, aside from analyze what happens in the transit with the new grid forming model, is to try it with 85% of participation. Okay, next steps for us is continue modeling the Chile Power Grid. Continue developing the model of the power grid. We're going to use this method of moving everything automatically from Power Factory to EMTP, but looking forward to update our CIM model. We decided to go with SQL and CGMS because, well, in Europe, they're all using it. The online static connection tool is going to be released to the public probably in August. The DSA of the digital twin is just starting. We need to meet for the kickoff meeting, but a lot of expectations from it. The grid forming models not only need to be inserted into the power grid and we need to run more analysis, but also we're going to run some hardware in the test loops with these two vendors I mentioned. Yeah, that's it. That's it for now.